L, where J is less than L, D infinity is given by C infinity provided that lambda k is a real eigenvalue, and it is given by sum of C infinity and its conjugate provided that lambda k is a complex eigenvalue. Okay, theorem 4 gives asymptotic behavior of the condition number independent of direction of perturbation. It first states the generic situation, that is J star equals to 1. And in generic situation, we can observe linear growth of this condition number with increasing t. And for non-generic situation, we have asymptotic upper and asymptotic lower bound, and we can observe exponential growth of the condition number with increasing t for non-generic situation. Our last theorem gives asymptotic upper and asymptotic lower bound for the condition number independent of specific data. Here, for the lower bound, lambda I lies in the first subset of the spectrum, and lambda k lies in the last subset of the spectrum. But from both upper and lower bound, once again, we can observe exponential growth of the condition number for q greater than 1. Okay, now let's see a few numerical tests. In our first example, we consider a 2x2 skew symmetric matrix for our left plot and a 4x4 skew symmetric matrix for the right plot. And we plotted maximum of this quantity in 10,000 random sections of the matrix B. Here, these red points are the maximum of this quantity, and we can observe that these maximum of this value is very close to 1, and which satisfy on theorem 2, which was about the skew symmetric matrices. In our second example, we considered a 2x2 symmetric matrix for the left plot and a 4x4 symmetric matrix for the right plot. And we choose our initial value in a way to have the generic situation, which was given by theorem 4. Let me show you. Here, this is the generic situation, J star equals to 1, and to have this generic situation, we choose our initial value y0 in a way to have it in the rightmost eigenspace. And we plotted maximum of this quantity in 10,000 random selections of matrix B, and we can observe that maximum of this values with increasing t are asymptotically going to 1. So this is all. It concludes my presentation. Thank you for your attention. If you have any question, please feel free to ask.
If you have any questions, you can raise. Okay, if there are no questions, I thank the speaker, Asmin Paruk, for a wonderful talk on this perturbation, propagative, and solutions of linear and differential equations. Thank you very much. Next speaker in this session, Mr. Aditya Narayan Hisabia, National Institute of Technology, Meghalaya, Shillong. Welcome to the speaker, and the title of this talk is on algebraic and geometric properties of Laplacian semi-positive matrices. Welcome to the speaker.
So my name is Orthogonal Matrices. I am a research scholar in United Meghalaya. The title of my presentation is on algebraic and geometric properties of Ln plus semi-positive matrices. This is the outline of my presentation, starting with the introduction, followed by preliminaries, semi-positive matrices, Ln plus semi-positive matrices, then conclusion and references. Semi-positive matrices are the ones which map at least one positive vector to a positive vector, and non-negative irreducible matrices map every positive vector to a positive vector. In that way, semi-positivity of matrices can be seen as a possible generalization of irreducible non-negative matrices. Semi-positive matrices are also found useful in stability of matrices, game theory, linear complementarity problem, etc. Semi-positivity has also been studied in terms of any proper cone K. Such matrices are called K semi-positive matrices. In this paper, we're basically interested in Ln plus semi-positive matrices, where Ln plus is known as the Lorentz cone or a second order cone or Einstein cone. Ln plus is defined as the set of vectors x in Rn such that xn greater than equal to 0 and summation of I is equal to 1 to n minus 1 xi square less than equal to xn square. In this paper, we basically study two proper cones SA Ln plus and Ka Ln plus defined for Ln plus semi-positive matrix A. We also study diagonal and orthogonal Ln plus semi-positive matrices. In particular, we show that Ln plus semi-positivity of an orthogonal matrix depends on the sign of only one entry of the given orthogonal matrix. Now, let us look at some basic definition, starting with the definition of cone. A set K in I is said to be a cone if K plus K is a subset of K, and for every vector x in K and non-negative scalar alpha, alpha x is also in K. And the next definition is of a proper cone. Closed, pointed, and solid cones are called proper cones. Here, pointed means K intersection minus K is the zero set, and solid means it has a non-empty interior. Now, the dual of a cone K is the set of all vectors x in Rn which have a non-negative inner product with all the entries of K. And the dual of a cone K is denoted by K star. In a proper cone K, we can always find a partial order via this relation x less than or equal to y, which means y minus x belongs to K. Okay. Now, any vector x in a cone K is said to be an extremal if any other vector y satisfying this relation 0 less than or equal to y less than or equal to x is a non-negative multiple of x. Such vectors x are called the extremals of that cone K. Now, if a cone K in Rn has exactly a number of extremals, such cones are called simplicial cones. Like if a cone K in R3 has 3 extremals, this is a simplicial cone in R3. Now, a proper cone is said to be an ellipsoidal if there exists a symmetric non-singular matrix Q with inertia n minus 1, 0, 1. That means it has exactly one negative eigenvalue and corresponding unit vector U such that K is the set of vectors x in Rn with x transpose Qx less than or equal to 0 and Q transpose x greater than or equal to 0. Next, we discuss Rn plus semi-positive matrices, simply known as semi-positive matrices. Okay. Any matrix A is said to be semi-positive if there exists a non-negative vector x such that Ax is positive. Then such matrices are called semi-positive. That is, a matrix is said to be semi-positive if there exists a vector x in the non-negative orthant Rn plus such that Ax is the interior of Rn plus. Okay. Now, if A is a semi-positive matrix with no column related submatrix is semi-positive, such matrices are called minimally semi-positive. Well-known fact about minimally semi-positive matrices is that the square minimally semi-positive matrices are the inverse non-negative matrices. In this section, we discuss two proper cones, SARN plus and KARN plus. SARN plus is a set of vectors x in Rn for which Ax is in Rn plus. that is AX is greater than equal to 0, and KA Rn plus is the intersection of SA Rn plus with Rn plus, the non-negative orth hand. Now the first result here states that for every invertible matrix A, SA Rn plus is a simplicial cone with extremals A inverse EI. That is the column vectors of A inverse. This follows actually this follows from the fact that if A is invertible, SA Rn plus is of the form A inverse of Rn plus. Okay. Now the second result is that if A is minimally semi-positive, then the semi-positive cone Ka is simplicial, and these two sets, these two cones SARN plus and KARN plus are identical. And the third one says that if A is minimally semi-positive, the extremals of the semi-positive cone Ka are the column vectors of A inverse. Now, after knowing the first result, one may ask that is every simplicial cone is related to some SARN plus? The answer is yes. The last result states that for every simplicial cone K, we can find an invertible matrix A such that SARN plus and K are identical. Ln plus semi-positive matrices are also defined in a similar way. Any matrix A is said to be Ln plus semi-positive if there exists a vector X in Ln plus such that Ax is in the interior of Ln plus. And such vectors, if exist, are called semi-positivity vectors. Now, for any proper cone K, a matrix is said to be a K monotone matrix if Ax belongs to K implies Ax belongs to K. We are interested in Ln plus monotone matrices. However, the last result states that if K is a for any proper cone K and A is a K monotone matrix, then A is non-singular and A inverse of K subset of K. That means A inverse belongs to pi K. Now, this definition of K monotone and the result together imply that K monotone matrices are also K semi-positive. Next, we discuss the two proper cones, SA Ln plus and Ka Ln plus, defined in a similar way as SA Rn plus and Ka Rn plus. The first one actually follows from the fact that every ellipsoidal cone is of the form B of Ln plus for some invertible matrix B, taking A as B inverse, A is equal to B inverse, we get our first observation. And A, whenever A is invertible, SA Ln plus is of the form A inverse of Ln plus. From this observation, we get the second one. Now, if A is an Ln plus monotone matrix, then obviously A is invertible, and these two cones Ka Ln plus and SA Ln plus are identical. And from the second and third observation, we get the fourth one. That is, if A is an Ln plus monotone matrix, then Ka Ln plus, the semi-positive cone, is an ellipsoidal cone. Next, we discuss rank 1 as Ln plus semi-positive matrices. Okay. Now, since we know that every rank 1 matrix can be written as UB transpose. Okay. Now, if B belongs to Ln plus, then for every X is in the interior of Ln plus, Ax is of the form alpha U, where alpha is the inner product of X and B, and Ln and as Ln plus is a self-dual cone, alpha is obviously greater than equal to 0, and this from this we get that alpha U belongs to Ln plus and A is Ln plus semi-positive matrix. Here the first result states that for any semi-positive matrix, that is Rn plus semi-positive matrix A, the semi-positive cone Ka Rn plus is self-dual if and only if A is greater than equal to 0. That is, the entries of A are non-negative. Now, if you see that if A greater than equal to 0 means A belongs to pi of Rn plus. We have shown a similar result for Ln plus semi-positive matrices as well. That if A is a square Ln plus semi-positive matrix, then the same positive cone Ka ln plus is self-dual if and only if A belongs to pi k. That means that is A of ln plus is a subset of ln plus by showing the following are equivalent. Uh, the number one is Ka ln plus is self-dual. Second one is Ka ln plus is same as ln plus. Third one is ln plus. The Lorentz cone is a subset of Sa ln plus, and obviously the fourth one is A belongs to pi k. That is A of ln plus is a subset of ln plus. Next, we discuss ln plus semi-positive matrices having their last column in ln plus. Now, if a matrix have its last column in the interior of ln plus, in that case, A of En will be and in the interior of ln plus, and as En also belongs to the interior of ln plus, it gives A is ln plus semi-positive, and the same positivity vector is En. Now, the following result states that if the last column is in the boundary, then also the matrix is ln plus semi-positive. If one of the other column is in the interior of ln plus. Though the next column, next example, says that a ln plus semi-positive matrix may have no column in ln plus. Next, we discuss ln plus semi-positivity of diagonal and orthogonal matrices. A diagonal matrix D with diagonal entries D1, D2, Dn is ln plus semi-positive if and only if Dn greater than 0. That is, Dn is positive. Now, see, if Dn is positive, then the last column of the given diagonal matrix is in ln plus. So, and this kind of matrices are ln plus semi-positive. We have already discussed that. Now, if the given diagonal matrix is ln plus semi-positive, then by the definition, it's clear that Dn is positive. Okay, now we have also shown a similar result for orthogonal matrices. Though the proof is not straightforward, we have used the second lemma for that proof. The second lemma states that any vector in Rn, say x1, x2, that xn, there exists a vector z in the interior of that Lorentz cone Ln plus, such that the angle between x and z are less than pi by 4, if and only if the xn is positive. We have used this lemma to show that if A is a orthogonal matrix of order n, then A is ln plus semi-positive if and only if the nn entry, that is ANN, is positive. In this paper, we have studied two proper cones, SANN plus and KANN plus. Okay, and we have also studied the self-duality of the semi-positive cone KANN plus. We have studied ln plus semi-positivity of different matrix classes like rank or matrices having their last column in ln plus. We have also studied orthogonal and diagonal matrices. In particular, we have shown that orthogonal matrix, the ln plus semi-positivity of the orthogonal matrix depend on the sign of only one entry of the given orthogonal matrix. These are some references. Thank you.
Any questions from audience side? Okay. Can I ask you a question? So, what is the difference between K-unit and unit with the speaker unit?
Yes, sir.
And 8, 7, 8, I think I proposed that.
Yes, sir.
Yeah. Okay. Speaker number? Okay, anyway. No problem. Right. If there are no questions, I think the speaker once again. Mr. Aditya is here. The next speaker is Mr. from New Statistical Institute to Delhi Center. And the title of the talk is The Latest of Symplectic Eigenvalues and Electricity Type Theorem. I welcome the speaker, Mr.
Thanks for joining. I would like to thank the organizers for giving me this wonderful opportunity to let me present my work in this conference. The title of my talk is Derivatives of Symplectic Eigenvalues and Litsky Type Theorem. This talk is based on the joint paper with my PhD supervisor, Professor Tanvi Jain. I'll get started with some basic definitions. By S2 and R, we denote the set of 2n cross 2n real symmetric matrices. By P2 and R, we denote the set of 2n cross 2n real positive definite matrices. A 2n cross 2n matrix M is said to be a symplectic matrix if M transpose Jm equal to J, where J is the 2n cross 2n matrix given in the block form here. Here O is the n cross n zero matrix and In is the n cross n identity matrix. A fundamental result on symplectic matrices is known as Williamson's theorem, states that if A is any 2n cross 2n positive definite matrix, then there exists a symplectic matrix M that diagonalizes A in the following way. M transpose AM is equal to the diagonal matrix DD, where D is an n cross n positive diagonal matrix whose elements are arranged in increasing order. These numbers are unique in the sense that they do not depend on the choice of n, and we call these numbers symplectic eigenvalues of A. From classical linear algebra, the spectral theorem that we know of is very similar to Williamson's theorem. Spectral theorem says that A can also be diagonalized using an orthogonal matrix, and in Williamson's theorem, we have a symplectic matrix instead of an orthogonal matrix. And the diagonal elements we get from spectral theorem are called the eigenvalues, and the diagonal elements here we call them symplectic eigenvalues. So in that sense, symplectic eigenvalues and eigenvalues are analogous notions, but both are fundamentally different. For example, A has size 2n, so it has 2n eigenvalues, but only n symplectic eigenvalues. Okay, moving on. Symplectic eigenvalues have applications in various fields of mathematics and physics. Perhaps the most important application is in quantum information theory, where one deals with quantum states. And associated with every n-mode quantum state is a 2n cross 2n positive definite matrix known as the covariance matrix of the state. Among all the quantum states that have been studied, Gaussian states are the ones that are of particular interest because of their mathematical formalism available. In particular, symplectic eigenvalues play important role in completely characterizing many important properties of Gaussian states. To give you a few examples, we have Heisenberg uncertainty principle, which states that a positive definite matrix A is the covariance matrix of some Gaussian state if and only if all its symplectic eigenvalues are greater than or equal to half. There are several entropy functions which are useful in giving measurements such as degree of entanglement and degree of mixedness. And these entropy functions can be written as smooth maps of symplectic eigenvalues of the covariance matrix of Gaussian states. In particular, we have this von Neumann entropy for a Gaussian state. If A is the covariance matrix of a Gaussian state, then the entropy function, the von Neumann entropy function of the Gaussian state is given by this expression. And this is a smooth map of symplectic eigenvalues of A. So, owing to various applications and importance, several quantitative results of symplectic eigenvalues have been studied in the past. These include perturbation theorems, majorization inequalities, variational principles, and so on. While studying these properties, there was some things missing in the literature, and what that thing is is the following. Recall Williamson's theorem. Given a positive definite matrix A, we get n unique numbers, d1 up to dn. So as a consequence of Williamson's theorem, we get n real-valued maps on the set of true and cross true and positive definite matrices. What we didn't find in the literature was any explicit study of qualitative properties of the symplectic eigenvalue maps, such as their differentiability, their analyticity, and so on. So we became interested in studying those properties, and we got several interesting results in this direction. So here's the overview of the talk. We shall first talk about differentiability of symplectic eigenvalue maps as functions of positive definite matrices. We then talk about differentiability and analyticity of these symplectic eigenvalue maps as functions of positive definite matrices lying on a curve. Then we give a fundamental class of inequalities between symplectic eigenvalues of A, B, and their sum, which is an application of our analysis. Now, one could ask a natural question. The natural question is, we know that symplectic eigenvalues and eigenvalues are analogous notions. So is there a mathematical connection between them? And if there is some connection, can we exploit that connection to study the behavior of symplectic eigenvalues using the theory of eigenvalues? Well, the answer is yes, there is connection. It is given as follows. If D is a symplectic eigenvalue of A, then plus minus D are eigenvalues of the Hermitian matrix iota A power half J power half, and they're also eigenvalues of the matrix iota JA. In fact, this connection of symplectic eigenvalues with eigenvalues of these matrices has been used in the literature, and those quantitative properties that we described earlier have been studied using this connection. So in principle, we could also use this connection to study the qualitative properties of symplectic eigenvalues that we are interested in, but it turns out this approach is not feasible in practice. For one thing, if you treat symplectic eigenvalues of A as eigenvalues of this matrix, we know that this matrix is not even normal. So, and there is no rich theory for eigenvalues of non-normal matrices. So this approach doesn't give us much. If you treat symplectic eigenvalues as eigenvalues of this Hermitian matrix, this approach also doesn't work because as far as differentiability is concerned, when we go for computing derivative expressions for symplectic eigenvalues using this connection, we would inevitably have to encounter differentiation of the matrix square root map, but there is no closed form derivative expression for this map. So as far as computations are concerned, using this connection also doesn't give us much. So because of these complexities, there is a need to develop an independent theory for symplectic eigenvalues, and that is precisely what we did in our paper. Let's talk about the differentiability now. We recall that the symplectic eigenvalue maps are real-valued maps on open subsets on the open subset, so it makes sense to talk about their differentiability. It turns out that they are not differentiable in general, which can be seen from the following simple example. Symplectic eigenvalues are not differentiable, but is there any condition which can guarantee their differentiability? Again, the answer is yes. Before that, we have this definition. We define multiplicity of a symplectic eigenvalue D to be the number of times it is repeated as a symplectic eigenvalue of A. And we say that symplectic eigenvalue D is simple if there is exactly one symplectic eigenvalue of A equal to D, the rest all are different from T. We have the following result on differentiability of symplectic eigenvalues. If the J symplectic eigenvalue of A is simple, then one can guarantee the differentiability of the J symplectic eigenvalue map there exists a neighborhood of A such that the symplectic eigenvalue map is not only differentiable, but it is a smooth map as well, meaning it is infinitely differentiable. We were also able to find the derivative expression for the jth symplectic eigenvalue map in this case. So the condition that jth symplectic eigenvalue map is simple guarantees the differentiability. It's more than that, it's infinite differentiability. But in general, we know that symplectic eigenvalues are not differentiable. So what we do is we relax the condition on the domain of symplectic eigenvalue maps. So instead of considering the entire positive definite matrices space, we consider curves in positive definite matrices, and we get several results there as well. If A is a curve of positive definite matrices such that it is differentiable at a point, then we can find n real valued maps that are also differentiable at t naught, and evaluated at t, these n numbers give the symplectic eigenvalues of A. Here we have used this notation d1 tilde up to dn tilde to emphasize that these n numbers are not necessarily in the increasing order that we get from Williamson's theorem. Furthermore, if this curve is assumed to be first order continuously differentiable, then there exists continuously differentiable symplectic eigenvalue maps in this sense as well. Now, when we consider a better assumption such as analyticity, we get further interesting results. If the curve A is assumed to be real analytic on an interval, then one can find real analytic symplectic eigenvalue maps as before. But again, these numbers are not necessarily in any particular order. But what can we say about the symplectic eigenvalues if we consider a particular ordering, say increasing order? We still get something nice if we consider any closed subinterval AB of the interval I, and djt is the jth symplectic eigenvalue of AT, then this map turns out to be piecewise real analytic on the subinterval AB as well. Now, this was a pretty interesting result because as a consequence of this, we were able to get something nice. We were able to prove that if A and B are any positive matrices, then the following set of inequalities hold. We take any k arbitrary indices, then the difference of the sum of the difference of symplectic eigenvalues of A plus B and A corresponding to these indices is greater than or equal to the sum of the first k symplectic eigenvalues of B. Now, this result is a symplectic analog of a result known as Lipsky's theorem for eigenvalues, which is a non-trivial result for eigenvalues as well. And the proof of this result uses our analysis, in particular, it uses piecewise analyticity of symplectic eigenvalues. This set of inequalities for symplectic eigenvalues, these generalize some previously known inequalities. Here are a few of them. Hiroshima's inequalities given by this set of inequalities can be obtained from the Lipsky type theorem by considering k indices 1, 2, all the way up to k. And this is what we get. Similarly, there is another set of inequalities given recently, which can be obtained from the Lipsky type theorem by considering k equal to 1. There are several other interesting questions one could look into. The questions similar to what we already have for eigenvalues, and there are many interesting results available for symplectic eigenvalues, and one could also look for other interesting results as well. Very recently, several weaker differential notions of symplectic eigenvalues have been investigated. Questions such as directional differentiability of symplectic eigenvalues have been addressed. the first order directional differentiability of symplectic eigenvalues has been established, and the expression for the first order directional derivative of symplectic eigenvalues have been computed. When we for eigenvalues, we also have the second order directional differentiability result and the corresponding derivative expression. One could also look for second order directional differentiability of symplectic eigenvalues and try to compute the derivative expressions for symplectic eigenvalues as well. So this is one of the open problems, one of the research problems one can try in this direction. One would also look for several quantitative results, such as we have several inequalities for symplectic eigenvalues. One could also look into conditions for equality in those inequalities. Again, similar results for eigenvalues have been established. So it would be really interesting to look into those type of problems that we have for symplectic eigenvalues. I would end my talk here. Here are some references that we found useful while working in these problems. Uh, Thank you very much for listening into the talk. And if you have any questions.
Any questions from audience? Okay, there are no questions. I think the speaker is Sumant Kumar Misra. That was a wonderful talk on derivatives of symplectic eigenvalues. Thank you.
Thank you.
Thank you all the participants. I also thank Professor Kunjam Shan Prasad for chairing this session. Thank you, sir. We'll start the next session at 15:10 IST. Good afternoon, everyone. Everyone. Welcome back, everyone. So now in this session, we have a contributory talks from Ms. Pallavi P. from Manipal Institute of Technology, Mahi Manipal. She will deliver a talk on different classes of prime hyperideals on hyperlattices. Another speaker of this session is Tapati Sahu from Manipal Academy of Higher Education, Manipal. Topic of our presentation is partial order on matrix maps over generalized rings. And the last speaker is Ms. Savita V. from Manipal Academy of Higher Education, Manipal. She will deliver a talk on generalized core-nilpotent decomposition. I now request Professor Sudhakar G. from MIT Mahi Manipal to chair this session. Over to you, sir.
So I invite Pallavi to present.
Good afternoon, everyone. I am Pallavi P., Research Scholar, Department of Mathematics, MIT Manipal. I am here to present a small talk on different classes of prime hyperideals in hyperlattices. These are the contents of my presentation. So when we listen to the word algebra, the word that comes to our mind is group theory. That is a good old friend, group theory. Group theory deals with the subjects like the system or symmetry that is present in the system. Whereas lattice theory is that branch of mathematics that deals with the order that is present in the system. So we can see this is a diagram of a lattice here. So if we see that, then we can see that there are elements, and we can see that 0 is situated below A. So it has some order. So what is a lattice? If we see the formal definition, lattice is a structure with two binary operations, meet and join, such that they satisfy associativity, commutativity, and absorption identity. And there is one notion of hyperstructures, wherein the composition of two elements constitutes a set. So, using this notion, the concept of hyperlattices was introduced. What is a hyperlattice? We know that in a lattice, classical lattice, there are two binary operations, meet and join. Here, one of the binary operation is converted into hyper operation. That is, join we are keeping as a hyper operation, and the meet is returned as a classical operation. And so, with these two operations on a set L, if these properties are satisfied, then we call that lattice, that structure as a hyperlattice. So the first property is that x belongs to x join x and x is equal to x meet x, and second is the associativity of the operations, and third is the commutativity of the operations. Next, we can define the order relation using the classical operation meet on this set H. So with respect to that order, we can see that the H together with that order becomes a coset. Throughout the further slides, we will denote that H for a joint hyperlattice. Yes. So now let us see some substructures in a joint hyperlattice. A non-empty subset I is called an ideal if any two elements are in J, implies that then that their join is in J, and second condition is that L1 belongs to J, and any element L2 is less than or equal to L1, then L2 belongs to J satisfies. If these two conditions are satisfied, then we call that set J as an ideal. Next, we can see the conditions for an ideal, hyperideal to be prime. If L1 L2 belongs to X such that their mate is in the ideal J, then if L1 belongs to J or L2 belongs to J satisfies, then we call such ideal as a prime hyperideal. And there is this notion of distributive lattices. This condition. The first condition is the classical mate is distributive over the hyperoperation join. This condition, and the second condition is that the hyperjoin is distributive over mate. In the classical case, these both conditions coincide, but in the case of hyper lattices, these conditions are different. Next, please define some notions, some generalizations to the concept of hyperideals. The first one is the concept of two-absorbing hyperideal. A hyperideal J is called two-absorbing if three elements, we have L1, L2, L3 belongs to the set H, such that their mate is in J, then either L1 mate L2 belongs to J or L2 mate L3 belongs to J or L1 mate L3 belongs to J. If this condition is satisfied, then we call such an ideal as a two-absorbing hyperideal. One thing to observe here is that every prime hyperideal is two-absorbing. Next, we know that intersection of two ideals will be a hyperideal. Now, if we have two prime hyperideals, Q and Q dash, then their intersection will not be a prime hyperideal, but the intersection will be a two-absorbing hyperideal. This is a proof of that statement. Next, we define a radical of an ideal. So what is a radical? We have seen this notion in algebra everywhere, like rings and other places. So what is a radical of a hyperideal? It is nothing but the intersection of all prime ideals containing that J. So if there is no prime hyperideal containing J, then we take the radical as the whole set H. So let us see an example. This is an example for a joint hyperlattice where the operations join and meet are given by these tables. Yes. And this is a table, this is a diagram representing the hyperlattices. Usually we cannot represent the hyperlattice with a diagram, but we have there are some classes of hyperlattices which we can represent through a diagram. So we have made an attempt to represent some special classes of lattices, hyperlattices through an example, through a diagram. So if we see if we want, we know that in case of joint hyperlattice, the hyper operation, join is a hyper operation and meet is a classical operation. So if we want the meet of two operations as two elements, say L1 and L2, then it will be nothing but the element. L1 meet L2 will be the one situated between below those two and where the line starting from L1 and L2 meet. So this will be the position. And if we want the join of these two elements, L1 and L2, this will be, the operation is a hyper operation, that is it will be mapping to a set. So we will be seeing above as in case of classical lattices, but this output will be set L3. Similarly, if we want the join of 0 join L2, then it will be the set L2 L3. So this representation will be convenient for us to understand the properties of hyperlattices better. Next we will see that if our hyperlattice is S-distributive, then J will coincide with its radical. Next, this is one more example for a join hyperlattice. The hyper operation is given here and the classical operation is given here. Then J is equal to 0, AB, CF will be ideal and its radical is different here because this lattice is not S-distributive. And this is the diagrammatic representation for that hyperlattice. These are some properties of hyperideal. And the first three properties of this are straightforward verification. The fourth property, that is radical of J intersection J dash is equal to radical of J intersection radical of J dash. Its proof is here. Next, using the definition or using the concept of radical, we will give one more generalization to the concept of prime hyperideals, that is primary hyperideal. Wherein, if we take we take two elements L1 and L2 such that the meet is in J, and we define the condition for primary hyperideal as whenever L1 meet L2 belongs to J, then L1 belongs to J or L2 belongs to the radical of J. So from the definition itself, we can observe that every prime hyperideal is a primary hyperideal. Next, we have a theorem. Let J be an ideal such that radical of J is prime if and only if the radical of J is primary. Next, we define one more generalization to the prime hyperideals, that is two-absorbing primary hyperideal. That is the meet, if L1 meet L2 meet L3 belongs to J, then either L1 meet L2 belongs to J or L2 meet L3 belongs to the radical or L1 meet L3 belongs to radical. every primary hyperideal as well as every two-absorbing hyperideal will be a two-absorbing primary hyperideal. Yes. Next, there is a theorem. If we have two hyperideals such that radical J and J dash are two hyperideals, and radical of J is a prime hyperideal and radical of J dash is also prime hyperideal, then their intersection, that is J intersection J dash, will be a two absorbing primary hyperideal. So this is the proof of that theorem. Yes. Next part, we define the annihilator of an ideal relative to an element X and this relative to an ideal I. So the annihilator of an ideal J with respect to X is defined as set of L1 in H such that L1 with X is inside J. Similarly, if J is zero ideal, then this will be the definition of the annihilator of zero with respect to X. Next, this is the annihilator of J with respect to the ideal J dash, where it is defined as L1 belongs, set of all L1 belongs to H, such that L1 with L2 is in J for every element L2 of J dash. We can see that if every ideal I, for any ideal I and element X belongs to H, the I will be contained in this annihilator of I with respect to X. Next, in a distributive hyperlattice, this set J dash, that is annihilator of J with respect to J dash, will be in H. Next, the mean distributive element is defined as follows. So whenever the X is a mean distributive element, then this set will be an ideal. That is, I is to X will be an ideal, will be a hyperideal. Sorry. Yes. Now, whenever J1 is a hyperideal, then its annihilator with respect to any ideal, provided J1 is not contained in J2, whenever J1 is a prime hyperideal, we will get that J1 is equal, annihilator with respect to J2 will be equal to the hyperideal J1. Similarly, whenever I is a prime hyperideal and X is a mean distributive element outside I, then this set will be equal. Next, we will see that if J is a X is a mean distributive element and J1 is two absorbing hyperideal, then the annihilator of J1 with respect to X will be a two absorbing hyperideal. This is a proof of that theorem. Next, similar to the previous case, whenever the ideal hyperideal is primary hyperideal and X is not in radical of J1 is a mean distributive element, the annihilator of J1 with respect to X will be a primary hyperideal. So we have seen that annihilator of hyperideal will preserve that two absorbing and primary nature in the annihilator case also. Next, we have a small proposition, that is, if J1 is contained in union of two ideals, then that J1 will be contained in one of them, either J2 or J3. Now, this annihilator properties and the two absorbing primary ideals are linked in this proposition. That is, these conditions are equivalent. That is, J is two absorbing primary, and if L1 L2 belongs to J such that their meet is not in radical of J, then these contained in relations we will be getting. And the fifth condition is that if J1, J2, J3 are ideals of H such that J1, J2, J3, the intersection is in J, then J1 intersection J2 is in J, or J2 intersection J3 is in J, or radical of J, or J1 intersection J3 is in radical of J. So this is somewhat similar to the condition of two absorbing primary in case of, in terms of the radicals also, in terms of ideals also. So these are some references. Thank you for your patience, Rifren.
Hello. Any questions from audience? If there is no question, we thank the presenter.
Next presenter is Tapti Sahu from Manipal Academy of Higher Education, Manipal. She is presenting a talk on partial order and matrix maps over generalized strings.
Good afternoon, everyone. Myself, Tapti Sahu from Department of Mathematics, MIT Mahi Manipal. And the title of my presentation is Partial Order and Matrix Maps over Generalized Strings. These are the keywords of my presentation. That is nearing, which is a generalized string, M group, that is modular over a nearing, matrix nearing, MNN group MN, partial order M group, positive cone, convex ideal, and partial order MNN group MN. I'll start with a natural example. Let G be an additive group, not necessarily abelian. Then Mg is the set of all mapping from G to G with pointwise addition and composition which satisfy all the axioms of ring except classes abelian and the left distributivity. Geometrically, if we consider all such linear map, that is f of x is equal to ax, then it satisfies both the left as well as right distributive law. Whereas if we consider the affine maps, then the left distributivity does not hold. So nearing is the study of nonlinear functions which generalize the ring structure, that is more formally n with two binary operation plus and dot, where n plus is a group, not necessarily abelian, dot is associative and it satisfies right distributive law, then such system is called right nearing. Here in particular we are taking the right nearings. And in right nearing, n0 need not be equal to 0 for some n belongs to n. For an example, in Mg, if we consider f of x is equal to a, which is non-zero, then if we consider f composition 0 at x, this is equal to a, which is non-zero. So it is a well-known fact that every ring can be embedded into endomorphism of abelian group, whereas nearing can be embedded into Mg, where G is just a group. So ring can be a nearing, but the other will not be true. For an example, let G be a group with at least two elements. Fixing a non-zero element A in G, if we define the map Fa, Ga and Ha at x is equal to A, then the left-hand side of the left distributive is equal to A, whereas the right-hand side is equal to A plus A. So it is not true as A is non-zero. So Mg is a right nearing, but it is not a ring. Now we define the M group, that is modular over a nearing. Let G plus be a group and M be a nearing, then G is called a left M group if there is a nearing homomorphism from M to Mg. More formally, G plus is called a M group if there exists a mapping from M cross G to G which satisfy following two conditions. Here M acts on left. Actually, every group G is an Mg group, every nearing is an M group over itself, and each left module is an R group. Now, in case of ring, matrix ring can be constructed as an arrays wherein the elements are from the ring, but in case of matrix nearing, it is not possible as due to the non-linear nature. For that, we need maps. Now, how we construct the maps is, we consider a right nearing with identity, Mn is the direct sum of n copies of n plus, then the ith injective, jth projective and the inclusion map is defined as follows, and the composition of all three maps is Fij which is from Mn to Mn, and the subnearing generated by all such function Fij is called the matrix nearing, and we denote it as MNN. So the maps has defined in such a way that if n becomes a ring with identity, then MNN becomes a matrix nearing, a matrix ring, and the additive group Mn becomes the MNN group in a canonical way. Now, if we consider a 2 by 2 case, we shall represent A as the sum or product of all such function, then A can be represented as the column follows. Now, Morita equivalence. Two unital rings are Morita equivalent if they have equivalent categories of left module. If A is a left R module, then AN becomes the MNR model in a canonical way, which preserves the homomorphism. So this analogy motivates us to study the interrelation between the M group over N and the MNN group MN. Some proposition, if I is a left ideal of N, then IN is the ideal of MNN group MN. And for any ideal I of MNN group MN, we write I star star is equal to A belongs to N such that A is the Z projection of A for some A belongs to I. And I star star also can be written as follows, and it becomes the left ideal of N. Now we define partial order nearing and partial order matrix nearing. N with less than equal to becomes a partial order nearing if N plus is a partial order group and the product monotonicity hold as they have shown here. Let N be a partial order nearing with 1, then for any AB belongs to MNN, we define the order between these two as A less than equal to B if and only if I projection map of A row is less than equal to I projection map of P row. For all row belongs to Pn power M, that the Pn is the positive cone of M. Then MNN with the less than equal to becomes a partial order matrix nearing if it satisfies the monotonicity in terms of product and the addition. For an example, let N be a fully ordered nearing, then the MNN matrix nearing is defined as follows, which is a partial order matrix nearing with respect to the operation. Here we can see that even if N is fully ordered, MNN may not be fully ordered. Here it is just the partial order. So this remark follows that MNN is fully ordered and not fully ordered in general, even if N is fully ordered. For an example, take M as the set of all integer, then N is fully ordered, whereas MNZ is not fully ordered. For an instance, if we take N is equal to 2, A is equal to F1 to 1 and B is equal to F2 and 1, then A at 1 1 is equal to 1 0 and B at 1 1 is equal to 0 1, but there is no relation between these two order pairs. Now we define partial order M group and partial order in MNN group MN. A partial order group G plus is called partial order M group over a partial order nearing if the product monotonicity hold, whereas in the second condition G1, G2 varies, that is the elements of G, and in the third condition elements of N varies. Let MNN be a partial order matrix nearing and MN be a partial order group. We define less than equal to MNN group MN as rho 1 less than equal to rho 2 if and only if the ith projection of A rho 1 is less than equal to ith projection of A rho 2 where A belongs to MNN. And the MN with less than equal to is the partial order MNN group if the product and the plus monotonicity holds. Here again rho 1 rho 2 varies, that is the elements of MN, whereas in the third condition A and V varies. If M is a partial order M group over itself, then MN becomes the partial order on MNN group. The positive cone of MNN group MN is defined as all such rows such that row is greater than equal to 0, and we define it as PMN will satisfy all four conditions. A subset T of an order N group is called convex if for all T1, T2 belongs to T and G belongs to G, T1 less than equal to G less than equal to T2 implies G belongs to T. If I is a two-sided convex ideal of M, then I star is a two-sided convex ideal of MNN. Now we consider a nearing M is equal to Z to cross Z which defined component wise and the less than equal to defined in N as follows, then M with less than equal to becomes a partial order nearing and the matrix nearing corresponding to M is MNZ to cross Z, that is defined as the sub-nearing generated by Fij AB where AB belongs to Z to cross Z, and corresponding to the convex ideal I1 that is 0 cross Z, we get the convex ideal I1 star in the matrix nearing. Now we define quotient partial order M group. Let G be a order N group and I be a convex ideal of G, we define the relation as x plus I less than equal to y plus I if x is less than equal to y plus I for some I belongs to I. An ordered matrix bearing MNN is called Archimedean if the additive group MNN plus is Archimedean, and Ln is convex and Ln if ρ1 ρ2 belongs to Ln and delta belongs to Ln, but ρ1 less than equal to delta less than equal to ρ2, then delta belongs to Ln. A matrix A is called sigma generated if it can be expressed as the sum of elements of Fij R where R belongs to M. And MNN is said to be sigma generated if every such matrix A is sigma generated. And M is said to be sigma generated if the corresponding matrix bearing MNN is sigma generated for all A n greater than equal to 1. Now I have listed some main results. If N is a fully ordered Archimedean, then MNN is fully ordered Archimedean and MNN is abelian. If L is a convex ideal of N, then the corresponding ideal Ln is convex in MNN group Mn. Similarly, if L is the convex ideal in MNN group Mn, the corresponding ideal L star star is convex in M. So there exists a one-one correspondence between the convex ideal of M and the convex ideal of MNN group Mn. Let Mn and N bar M be MNN groups. If F from N to N bar be N isomorphism, then there exists a MNN isomorphism from N into N bar N. Let N and N bar be partially ordered sigma generated near rings. If N by I is isomorphic to N dash by I dash where the order and the convexity preserves, then the corresponding matrix bearing MNN by I star is also isomorphic to MNN dash by I dash star. Here also the order and the convexity preserves. Now some application and future scope of the presentation. We can apply the partial order notion of N group over matrix bearing to play the interplay between the partial order prime ideals of Mn and the matrix MNN group Mn. Let 1 belongs to N and G be a multiplicative group with at least 2 elements, then we define the mappings Ng from N power G to N power G defined as follows. Then where Ng is the direct sum of cardinality of G copies of N plus, and the sum pairing generated by all such map is called a group pairing. That is, if mod G is equal to N, which is finite, then it will become the matrix pairing. So we wish to apply the partial order nature in terms of group pairing and proof characterizations. These are some references. Here are some publications related to this. Thank you.
Any questions from the audience? There is no question. We thank the presenter.
Thank you, sir.
And next presenter is Savita V from Manipal Academy of Higher Education, Manipal. She speaks on generalized core nilpotent decomposition.
So good afternoon. This is Savita V presenting a talk on generalized core-nilpotent decomposition. This work is along with my guide Dr. K. Manjunath Prasad and Uma Shankar Kerataya. These are the contents of my presentation. These are the notations which I use in my presentation. First, we come to the introduction. Given an M by N matrix A over a complex field, consider an N by M matrix D satisfying these 4 conditions. Whenever the matrix A is a square, the following matrix equations are considered along with these 4 conditions. Then the matrix G satisfying condition 1 is called generalized inverse of A, and an arbitrary generalized inverse is denoted by A minus. The matrix G satisfying condition 2 is called outer inverse of A, and an arbitrary outer inverse is denoted by A equal to. The matrix G satisfying conditions 1 and 2 is called reflexive generalized inverse of A, and an arbitrary reflexive generalized inverse is denoted by AR minus. The matrix G satisfying 1, 2, 4 is called Moore-Penrose inverse of A, and it is denoted by A plus. The matrix G satisfying conditions 1, 2, and 5 is called group inverse of A, and is denoted by A hash. The matrix G satisfying the condition 2, 5, 1 power K is called Racine inverse of A, and it is denoted by AD. So first we define some basic terms. Index of A is the smallest integer k for which rank of A power k plus 1 equal to rank of A power k. A matrix A belongs to Cn by n is said to be a core matrix if index of A equal to 1. A matrix A is said to be nilpotent if A power k is 0 for some integer k. A matrix A belongs to Cn by n is said to be EP if column space of A equal to column space of A star. A square matrix P is called projection matrix if it is equal to its square, that is P square equal to P, and it is called orthogonal projection matrix if P square equal to P equal to P star. So under matrix partial order I define minus partial order. For matrices AB belongs to Cm by n, we say that A is below B under minus partial order if there is a generalized inverse A minus of A such that A minus A equal to A minus B and A minus equal to B A minus, and we denote by this notation. For ABC belongs to Cm by n such that B equal to A plus C, the following statements are equivalent. A and C are disjoint matrices. Rank B equal to rank A plus rank C. A less than or equal to B under minus partial order. And class of generalized inverse of B is contained in class of generalized inverse of A. Similarly, this. The matrices A1 and A2 are said to be disjoint if their column space and row space are disjoints. If A equal to A1 plus A2, where A1, A2 are as in the above, and rank A equal to rank A1 plus rank A2, then the A equal to A1 plus A2 is called rank decomposition. We define the core nilpotent decomposition. Given us real square matrix A, there exist matrices CA and NA such that A equal to CA plus NA satisfying the following condition. Rank CA square equal to rank CA and NA to the power K is 0 for some integer K, and CA NA equal to NA CA equal to 0. Then the sum A equal to CA plus NA satisfying 3 is called co-nilpotent decomposition of A. And this type of decomposition uniquely exists. Next we come to core-EP decomposition introduced by Wang in the reference 8. Let A belongs to Cn by n, B with the index of A equal to K. Then A can be written as the sum of matrices CA and EA, where CA is a core matrix, EA to the power K is 0, CA star EA equal to EA CA equal to 0. Then the sum CA plus EA is called core EP decomposition. And this core EP decomposition of a given matrix is unique, and it is also a rank decomposition. Next we come to EP nilpotent decomposition. Let a matrix A belongs to Cn by n, B with index C equal to K, rank A equal to R, rank A power K equal to T. Then A can be written uniquely as the sum of matrices A1 and A2, where A1 is a EP matrix, A2 power K plus 1 equal to 0, A2 A1 equal to 0. Here one of both A1 A2 can be null. The sum A1 plus A2 is called EP nilpotent decomposition. And further, this EP nilpotent decomposition of a given matrix is unique, but it need not be a rank decomposition. Okay. So now we come to the process of generalizing core-nilpotent decomposition. So I restate the definition of core-nilpotent decomposition. Given a matrix A belongs to Rn by n such that A equal to A1 plus A2, consider the following conditions. The first one, A1 is a core matrix. Second one, A2 is an nilpotent. Third one, A1, A2 equal to 0. Fourth one, A2, A1 equal to 0. So then clearly, A equal to A1 plus A2 is a co-nilpotent decomposition and A1 is Ca and A2 equal to Na. Now we define A equal to A1 plus A2 is said to be orthogonal co-nilpotent decomposition if A1, A2 satisfy the conditions 1, 2 and 4. In addition, A1 star A2 equal to 0. And the decomposition is called OCN since column space of A1 perpendicular to column space of A2, which is same as the core OEP decomposition introduced by Bank. And A equal to A1 plus A2 is said to be EP nilpotent decomposition if A1 is an AP and A2 is nilpotent decomposition. The above definition of EP nilpotent decomposition is different from one introduced by Van and Leo. Now, in this process, we come across the few basic standard results. Let A and B be the matrices of size m by n. Then the following holds. First one, if column space of A and column space of B are disjoint, then rank A plus B equal to n minus dimension of null space of A intersection null space of B. In particular, if null space of A is a subspace of null space of B, then rank A plus B equal to rank A. The second one, if column space of B is a subspace of column space of A and row space of B and row space of A are disjoint, then rank A plus B equal to rank A. This is the theorem useful in our discussion. Let Ca be the core part in the core nilpotent decomposition of a matrix A and D be the index of A and A equal to A1 plus A2B such that A1 is a core matrix and A2 is an nilpotent matrix. The following statement hold. First one, if A to A1 equal to 0, then A1 is a matrix such that column space of A1 equal to column space of A power D equal to column space of Ca. And similarly, if A2 equal to 0, then A1 is a matrix such that row space of A1 equal to row space of A power D equal to row space of Ca. We come to classifying the generalized co-nilpotent decomposition. A matrix sum equal to A1 plus A2 is said to be generalized co-nilpotent decomposition of type 1 if A1 is a core matrix, A2 is an nilpotent matrix, and A2 A1 equal to 0. And it is said to be GCN2 type decomposition if A1 is a core matrix, A2 is an nilpotent matrix, and A1 A2 equal to 0. Now, for characterizing the GC1 of A, we consider the following property of the co-nilpotent decomposition. So, in the co-nilpotent decomposition A equal to Ca plus Na, Ca is given by A power dA, where A power D is the Drasin inverse of A, and Na equal to A minus A power dA. And if we consider Ca A minus Ca, so that will give us equal to Ca. This holds for all A minus. And therefore, it is clear that Ca less than or equal to A and a minus partial order. And now we consider the class C1 given by the class of matrices PA plus I minus PA, where P is any arbitrary oblique projection onto column space of C. And we got that if A is a matrix, then the class C1 defined above that is equal to the class A1 plus A2 belongs to GC1 of A with the condition A1 less than or equal to A and a minus partial order. So this class C1 satisfies the matrix decomposition. But now we consider this example, the matrix A given as a sum of these two matrices. So clearly this decomposition is in GC1 of A, but it's not satisfying the rank condition. This says that C1 is not characterizing GCN1 of A. So now we define the another class C2 as AP plus A into I minus P, where P is any arbitrary oblique projection onto column space of C. And note that in the above, P need not be dominated by A and a minus partial order unless row space of P is subspace of row space of A. So that the decomposition in C2 need not be rank decomposition. And we can prove that given a square real matrix A, GCN1 of A is equal to C2. So now if we extend this result to our rings, in the case of an associative ring through, we could define a right index of an element by the minimum of k for which a power k plus 1x equal to a power k for some x, and left index by the minimum value of k for which y a power k plus 1 equal to a power k for some y. And note that it need not be true that they are always same unless the ring is with bounded index of nilpotency. So before going to apply this result to the ring, elements in a ring, we define the few definition. Given an element A from an associative ring A is right or left biregular if there exists a positive integer k and an element x belongs to the ring A or y belongs to A such that a power k equal to a power k plus 1 x or a power k equal to y into a power k plus 1. So in which case x or y is called right or left pi inverse of A. And pi r of A or pi l of A denotes set of all right or left pi inverses of A, and the least k for which x belongs to pi r of A, y belongs to pi l of A is called right or left index of A. The necessary and sufficient condition for having generalized co-nilpotent decomposition in case of ring is as in the following theorem. So given an element A from an associative ring A, the following statements are equivalent. The element A has generalized co-nilpotent decomposition of the form A equal to B plus C, where B is with the right index 1, and C is such that C power k equal to 0 and CB equal to 0 for some positive integer k. Second one, element A is a right biregular with right index n, and there exists beta such that a power n equal to a power n beta a power n minus 1. In the above cases, the least integer k satisfying 1 is the right index of A appearing in 2. So with this result, I end my talk. These are my references. Thank you.
If there is no question, we thank the presenter. Hello? Hello? Madam?
Yes, yes. If the road one is there, if not, he has related with some Spanish people.
Ma'am, can you please repeat the question?
Hello?
Saroj Malik has related
Is it? The question is not clear.
Saroj Malik
Okay, thank you for the reference. Thank you all the contributory speakers. I also would like to thank Professor Sudhakar ji for chairing this session. Next session will start from 16:30 IST. I request all the participants and delegates to join the link with the name CRR Hall. Thank you.